Hello, everyone. We're very excited to be here talking to you today about novel and enhanced regolith uplift technologies. My name is Andrew Scott George. I'm a researcher at the University of Glasgow. So specifically, we're going to be having a conversation about three concepts that are intended to uplift surface regolith from the lunar environment. These concepts are shaped by three key drivers. One of them is the lunar regolith itself. It's a tricky material to work with. It's cohesive, it's abrasive, and it's liable to become compacted, which will again increase bulk density, penetrative forces. We're also contending with the lunar environment. So of course, vacuum, microgravity, and electrostatic charging will influence not only the properties of the regolith, but its interaction with your concept. And finally, the concept will need to make do with very limited resource. We're thinking typically in terms of power, heat, and mass, but also quite crucially in this context, the mechanical force that the rover can invoke. So with that said, I'll now present the first of the three concepts that we explored. The first concept is an enhanced form of scoop. So this is in some way the established and most widespread approach to this problem. We've seen its use in the Mars Phoenix lander. And probably the main vulnerability for doing things this way is going to be the force of breaking into compacted regolith. So we've proposed two mitigations, two ways to work around that. One is to optimize the geometry of your scoop, the geometry of the blade. And two is to apply vibration. So when you vibrate a tool, it can fluidize a boundary layer of regolith around it, which can locally reduce penetrative forces. So to explore these things, we developed four scoop geometries with roughly equivalent footprint and extent. And we procured a vibro motor so that we could compare the effects of vibration. That was the first concept. The second one I'd like to touch on is a modified form of auger. So augers have planetary sampling heritage, normally in subsurface drilling for conveying core cuttings. We wondered if there was a way they might be adapted to uplifting surface regolith. So the first problem you run into is feed. How do you feed new material in if you're not pressing down into cut spoil? We realized we could actually harness the motion of the rover to drag the tool through that surface layer of regolith. So we're proposing a lateral feed of regolith into the inlet. And the second point was really what kind of architecture would be best suited to the properties of lunar regolith. And we came across this Australian invention. It's called the Olds elevator. It's essentially an inverted auger. So in your conventional auger, you have a rotating screw. Olds elevator, it keeps that screw stationary and it rotates a tube about the outside of that screw. It has been shown to perform well with cohesive materials, as we're expecting the regolith to be. It's volumetrically efficient compared to a typical auger. And because you now have a rotating external surface, you can put some useful geometry there, such as cutters that assist with feed and could also potentially break up compacted regolith. That's our second concept. The third one is a novel concept called the pulse elevator. It is essentially a solid state part with a series of internal bucket features. And the idea is when it's vibrated past a certain threshold, grains begin to leap from bucket to bucket and rise through the device. So we think it may be suitable for a few reasons. One is it's shown good performance with regolith materials before. Two is it could be drag fed again, although we may expect its performance to be even better in terms of feeding into the inlet because of that vibration effect, because of that fluidization of granular materials. It doesn't require any torque, so at least in respect to the regolith, so there's no torque for the rover to react. And there are rooms for power savings under microgravity. That threshold of vibration which is required, G is in that equation, so it should be lowered under microgravity. Those are the three concepts we wanted to explore. The question you raise is how do you test these things in a meaningful way? They all have quite different underlying principles as well as econops in which they might be used. So the first thing we did to bound it was define what does a test look like. In the case of a scoop, it would be to take a single peck of material. In the case of the drag-fed concepts, it would be to make a pass of a finite length, in our case, 30 centimeters. The question is also raised, how do you compare the performance of these things? So we've defined what an opportunity is for each of them. We might look at mass capture for a single run. We might also look at power draw, the power profile expended in doing that. So we tested it in our lab in ambient conditions. We used a variety of materials. We had one Lunar simulant, one South Pole simulant. We also had sand, which is comparably dense, but much better flow characteristic. We had kaolin clay, poor flow characteristic, but a lower density. And with lessons learned, we built towards a test in a dirty vacuum chamber in Glasgow. Could go down to about 1 Pascal. We brought along the South Pole simulant. We had limited access time to this chamber. So what we did was we developed the rig you can see up there, which allows for testing in parallel of the three concepts. Okay, so we've covered the concepts and their reasons. We've covered how we tested them, and I'll talk via each concept about what we found. So the scoop, the first thing I'll draw your attention to is the data set in the top right there. So you can see there's a column for each of the scoop geometries and one column for the vibrated version of the half spade scoop. One thing that became pretty clear is that the toothed concept seems to be doing very well. You can see it captured the most mass by some margin for the lowest current and the most consistently. It had the least spread. And I'll come back to saying that they had quite similar footprint and extent. There were some that had a slightly smaller footprint than the tooth, some that had slightly larger, and it's still doing well. Vibration seemed to have a positive effect, not in terms of reducing penetrative force, at least as seen by current, but more so in terms of the mass capture. There was 10% additional mass capture when vibrating a scoop as opposed to not vibrating it. In terms of the vacuum, the scoop succeeded in uplifting some material. Sadly, on the day, due to an equipment error, and really you can read human error there, we were current limited down to 1 amp as opposed to 3 amps, which we'd been used to testing at. Of course, we later verified these findings in ambient by putting that same current limitation in place, and it seems to be that the performance of the scoop was not impacted by vacuum positively or negatively. We can now come to the auger. So the first thing to note is that drag feeding was shown to be effective. You could laterally feed regolith into an Olds elevator and it would convey, as you can see in that GIF in the top right. To characterize the system, we're looking at a nominal power draw of around 5 watts at rest, 10 watts when conveying material. And over that 30 centimeter pass, it was able to capture about 114 grams of material at 2.5 grams per second, it works out. One thing we did note is that the insertion depth seems to be quite a sensitive parameter for this tool. So 25 millimeters was about the cutoff. If you didn't insert it 25 millimeters or more into the regolith, no material will feed. It's probably no accident that that's about the height of the inlet in this design. So there's implications for inlet design if this tool is being used. Now, okay, the vacuum test. Overall, an underwhelming result for this tool. It did succeed in uplifting regolith in vacuum on one test, but it was much less than expected, only 8 grams. And in one case, none at all. So we might wonder why this happened. We can at least partially explain this due to a drift in test conditions. So we were seeing some dispersion in the fill level of our regolith during pump down. And given we know that the insertion depth was quite critical for this tool to function, it's possible that that might have been at play. Hopefully, we will be getting more data points on this the next time we access the vacuum chamber to verify whether this is significant or not, because augers should work in vacuum. Okay, the pulse elevator. Once more, drag feeding was shown to be effective, but interestingly, not essential. So the pulse elevator, as you can see up there, was able to feed and eject regolith even without being dragged. And we think that's probably is due to the vibration fluidification of the regolith. To characterize it, nominal power of around 40 watts, 20 to 42 grams of capture in a single pass. You will note that the 40 watts is a fair bit higher than the other concepts. We think that's at least in part due to losses in the drivetrain. We built the vibration drivetrain ourselves. It's an early rig. There's probably quite a lot of losses in there. So in future, we'd be hoping to bring that number down as we improve it. And in a good result for it in vacuum, it succeeded in uplifting regolith, essentially in alignment with its performance in ambient. So those are individually the three concepts. We might now come towards summarizing what we've done and trying to position it within the field. We think this is a strong foundation for future research. As a technology demonstration, This is the first time the pulse elevator has been trialed in vacuum. It's the first time the OLS elevator has been applied to regolith and trialed in vacuum. So there's a couple of firsts in there. And look, broadly speaking, we gave each of these concepts a similar opportunity to uplift regolith, and to varying degrees with varying trade-offs, they all succeeded in doing so. We've contrasted sampling in motion as a ConOps with stopping and sampling, and we found that sampling in motion can be effective. You can drag feed established concepts such as the auger and novel concepts such as the pulse elevator. If we open ourselves up to sampling in motion, it really does broaden the range of technologies available and mission plans, ConOps available. We're already seeing research in this direction, such as NASA's Razor, and I think we can put this alongside that as a case for considering sampling in motion. And then just quickly coming back towards the scoop, look, scoops are going to be used for a very long time. We've seen within our experiments, within the geometries that we contrasted, a toothed scoop seemed to be quite effective with lunar South Pole regolith. And that vibration can perhaps improve your mass capture for the same power expenditure. So I'll thank you for your attention and your time. And just before going over to questions, I'll say we have a great deal of lunar simulant left over. We have access to a dirty vacuum chamber. And if you're interested in anything you've seen, or perhaps you have something of your own you would like to share with us, then please do reach out because we'd love to collaborate. Thank you.
Okay. Thank you very much, Andrew. Any questions? We have time for a few. But James at the front, yeah.
I may have missed this. Are these the scale that you see the devices being used at on the lunar surface, or would you go larger, smaller, and how do you foresee scalability changing?
That's a good question. I think terrestrially, the OLS elevator has been scaled up to like several meters height, possibly even up to 10 meters height. The pulse elevator, we've recently demonstrated up to 4 meters height. That's obviously a lot bigger than a rover is probably going to be, but you can imagine shared use for, say, like ISRU facilities. So I think there's certainly room to scale them up. Within the context of a rover, I think this was a sensible kind of scale to consider things. But yeah, there's room to explore them being upscaled. Thank you.
Hi, Francesco Ladini, Italian Space Agency. Very nice presentation. Did you envision any problem related to abrasion of the regolith, especially on the last two concepts, or jagging of any mechanism obstruction of the, if any bigger grain come into the feed, let's say, the way you collect it?
I'm sorry, was that concerning like abrasive effects of the regolith on the concepts?
The abrasive, property of regolith into, for example, the auger, if it can damage it, and if any particular, bigger grain could obstruct in some way the mechanism, such that it jags or it.
Yeah. Okay, that's a good question. So for the old elevator, compared to an auger, there is a greater space between the screw and the tube itself. So it's been shown to be more safe with various particle sizes. Obviously, it's easy to envision a situation in which a large particle becomes trapped. I would like to explore kind of passive filtration with, say, like a mesh cover at those inlets. Abrasive effects, I mean, sure, wear and tear is going to be a concern if these things are being used over the long run. In the context of these experiments, these were 3D printed devices and they worked and they didn't break, not that often anyway. Regarding the pulse elevator though, because I think it's worth mentioning, that has quite good particle size rejection because the inlet is a certain size, no particle is going to enter above that size. And because of the vibration fluidization effect, you don't see any kind of clagging or blocking happening there. And in a result of kind of accidental beneficiation, the slide's gone now so you can't see it, but because of a slightly loose seal on the two halves of the pulse elevator, we saw very fine particles being ejected from the side as well, like fine dusty particles. So we did have large particle rejection at the front and small particle rejection from the side. Now that was an accident, but maybe it's interesting.